Welcome to the Farm Bits Podcast, a product of Nebraska Extension Digital Agriculture. I'm Jackson Stansel.
And I'm Samantha Teaton, and we come to you each week to discuss the trends, the realities, and the value of digital agriculture.
Through interviews and panels with experts, producers, and innovators from all sectors of digital technology, we hope that you step away from each episode with new practical knowledge of digital agriculture technology. Hello, and welcome to the 38th episode of the Farm Bits Podcast. As you may notice, if you're watching the video or if you're just on audio, you may be missing Samantha's voice. For the first time, I'll be hosting a Farm Bits episode solo. As you may have heard, if you listened to our last episode here on the Farm Bits podcast, Samantha has completed her master's degree and has started a position as a developmental agronomist with Golden Harvest. Samantha made a significant impact on many people during her graduate program, and she will certainly be missed on our team. And I know that I'm missing co-hosting with her for this episode, and I will in the future for all of our future episodes as well. But we're very excited to see what she does next, and we look forward to having her on the podcast in the future or just hearing more from her and obviously staying connected. So if you'd like to stay connected with her as well, make sure you follow her on Twitter. And it sounds like she may even be releasing a podcast through Golden Harvest. And so we will do our best to share that information with you as it becomes available to us. This episode marks the conclusion of our nitrogen management series, and the focus of this episode is measuring nitrogen in the soil. I'm pleased to welcome Dr. Jonathan Claussen as our guest for this episode. Dr. Claussen is an assistant professor in the mechanical engineering department at Iowa State University. His research focuses on nanotechnology and sensor development with a multidisciplinary focus that includes both biomedical and environmental applications. To date, there have been very few, if any, robust soil nitrogen measurement sensors that have made it to the market, and we wanted to get Dr. Claussen's perspective on what makes nitrogen so hard to measure in the soil, and his insight from his lab group's innovation and their work on developing a sensor to overcome these challenges. So, without further ado, let's get to it. Here's my interview with Dr. Jonathan Claussen.
I did my undergraduate degree at the University of Minnesota in mechanical engineering. And then I went on to Purdue University to do my graduate education. And there I was always interested in trying to learn more about nanotechnology and apply that to biological types of sensors. I was really interested in biomedical diagnostics to begin with, but then it kind of brought into the environmental sensors and some of the sensors we'll talk about today. But I did my master's in mechanical engineering at Purdue, and then my PhD in biological engineering to gain a little more insight into biological devices and biology in general. And then I went on to do a postdoc at the University of California, San Diego, in their nanotechnology department.
Cool.
And then after that, I went ahead and did a postdoc at the U.S. Naval Research Lab in Washington, D.C. on more about nanosensors and biology. And then in 2014, I ended up in Iowa State University as an assistant professor.
Awesome. So I guess you do a lot of different types of research. You mentioned biological and kind of the biomedical side of engineering, and you mentioned the environmental side. How exactly is that breakdown right now in terms of your recent research since you've become an assistant professor at Iowa State?
Yeah, I definitely have gotten a lot more into the environmental sensing. I guess it kind of makes sense since Iowa is more of an agricultural based state in terms of its workforce and so forth. But yeah, so we do have some biomedical sensors. We're doing some wearable sensing to look at hydration and fatigue levels in sweat. But then the majority of that beyond that is kind of environmental sensing. So we have a USDA NIFIC grant to look at a nutrient sensing in or pesticide sensing in the environment and crops and so forth. Then an NSF grant to look at nutrient ion sensing in soils, and also grants to look at salmonella in other foodborne pathogens in food products, and also looking at cattle disease biomarkers for Johne's disease. So yeah, we've really kind of from farm animals to crops to safety, food safety. It's really revolved a lot around agricultural
Yeah.
products and sensors.
Absolutely. Yeah. It seems like you're really diving into the food system quite a bit. And I guess I saw an article, and Samantha, my former co-host as well, she saw an article that suggests that you'd been working on this, nutrient sensor for the soil, specifically for nitrogen. And nitrogen is kind of the focus of the series that we're in now. So why exactly did you decide that you wanted to begin working on measuring nitrogen in the soil profile? And how did that collaboration, come about, that collaborative research venture?
Yeah, absolutely. Yeah, it was, it's a huge issue. And it's pertinent to Iowa. Iowa, southern Minnesota, and Illinois really are three of the largest nutrient runoff producers, if you have, from their farms into the Mississippi watershed.
Sure.
So it's, we hear about it often in the news. And and I have worked on ion-selective sensors before. Some of our wearable sensors are detecting potassium, chloride, and sodium in sweat. And it seemed to us that we could use similar technology to detect nitrite, nitrate, and ammonium, and potentially phosphorus in soils as well. And they worked really well. Our initial lab results, we were so impressed that because they're working better than some of the commercial sensors that we could buy, and they're
Huh.
holding up longer. And a lot of the commercial sensors are geared for working in water
Sure.
and kind of in a pristine environment. So we realized that more engineering had to be done to make them more robust to actually work in the soil environment or soil slurries.
Sure. So is that the overarching goal of the project, was to specifically develop that sensor and then also offer some kind of robust testing, or was it just laboratory testing? Did you get in the field? I guess what was kind of the scope of the project?
Yeah, absolutely. So it's ongoing. We have tested it in the laboratory in various soil slurries that would mimic the water content that you would find in the field.
Sure.
And we're a little bit delayed because of last year, the pandemic.
Yeah.
But this spring, as you can imagine,
Yeah, absolutely.
but, but this spring we're putting out sensors into two watersheds in Iowa. So that would be in water, and then also we're going to we have a housing to actually put it in a soil probe and bury it at depth in some farm fields as well. So we both want to monitor in kind of a completely aqueous water environment as well as soil and in farm fields.
Awesome. And I imagine that's kind of to capture both the runoff, the runoff side of nitrogen, as well as some of the leaching and nitrogen content for whoever's trying to manage nitrogen on that field. Is that correct?
Yep, exactly. The leaching and runoff, but it also can help the farmer know, how much nitrogen is in that field, and now they have more and more equipment where they can deliver that fertilizer throughout the growing season, even to corn and soybean and other row crops. So this could be a way that they could gauge how much is there, and a third of their costs are roughly the
Yeah.
fertilizer inputs. So if they can use less fertilizer and maintain their crop yields, that's a win-win for the farmer and for the environment.
Absolutely. So I guess getting into the sensor a little bit more, and specifically measuring nitrogen, these ions that you mentioned earlier, what exactly is it that makes nitrogen so hard to measure in general? And as you mentioned, I guess it's a little bit easier maybe in aqueous solutions, and some of the commercial products don't necessarily do all that well. And so what makes it really hard about measuring nitrogen in the soil specifically, for these sensors?
Yeah, yeah, exactly. So in the soil, all that particulate matter can foul or biofoul your sensor, and kind of within time prevent those ions from actually reaching your sensor and making a reading. So
Okay.
that's why in general it's more difficult than in water. The ion selective membranes we work with too do well when they're wet and they stay wet. But if they dry out and re-wet and then dry out, that's really that cyclical pattern of wetting it and drying it can really degrade that sensor quickly. And you kind of almost have to sometimes recalibrate it if it's been dry for too long.
Sure.
So those are some issues that may occur in a soil environment versus,
Sure.
the water environment.
Absolutely. So what exactly does this sensor, the device, look like right now that your team has engineered, and how is it kind of meeting some of those constraints?
Yep. So the sensors themselves are pretty small. They're the working part of that sensor is anywhere between 3 and 5 millimeters in diameter.
Wow.
And we have, so it's not too
No,
big.
not at all.
And then we have and then we have it next to a reference electrode that's about the same size.
Okay.
So you can imagine those little circular patterns on a single test platform device can be made for, one could be sensing ammonium, one could be sensing nitrite, one could be sensing nitrite, and so forth. Um, and so it is a small package, but what the hardware around it though is what is the bulk of it. So we need to interface it with these polymer plastics that we use to package it and make a watertight seal around it, so that the electrical connections can be made on the back end, and it can stay in the water or soil and not, and not have that water reach those electrical connections. And then we have to have
Sure.
battery technology, and then some sort of telemetry to, sometimes we can transmit that data wirelessly to, a central server and pick up that data or what have you.
Sure.
Yeah.
So how big are we talking as far as with all the hardware and everything included? Is this like a 6-inch sensor, like a box that you kind of bury, or what exactly does it look like once it's in that finished form?
Yeah, right. So in the field, it's more like a large stake.
Okay.
If you
Yeah.
could imagine a
Yeah.
probe, you could
Yeah.
drive into the ground,
Sure.
and it's like a hollow tube
Okay.
that's maybe an inch or two in diameter.
Sure.
And then it's filled. The sensors are on the edges, and the wires can go up. And then it's still pretty rudimentary because it's academic studies. So we'll just
Right.
have a battery pack on top, usually on top of the soil, and some electronics there. So that maybe is where the little box is.
Sure.
And then likewise with the water, we'll probably have a similar housing where it's just a tube a probe that would stick into the flow of that stream, and then
Sure.
have the electronic maybe on a dock or something.
Sure. So it works very similar to something like a watermark, or maybe some sort of capacitance probe for soil moisture that you would see out there commercially in the field.
That's right. Yep. It
Yeah.
looks very much like those capacitor and soil moisture probes. Yep.
Got you. So really a lot of the advances in the technology are centered around kind of this selective membrane that y'all are putting out there to select for these particular ions. So what exactly makes developing that membrane so challenging? And I guess what have been some of the innovative steps that y'all have taken to, make these membranes and truly be able to select for nitrate, ammonium, nitrite, and those sorts of ions?
Yeah, exactly. Yeah, there's a lot of different issues that go on in making those constituents. You need to have, it's a hydrophobic membrane that needs to allow the ions to pass through it. So it's kind of this porous network. And then you have ionophores that help shuttle those ions across that hydrophobic membrane to the sensor itself, so that a potential difference can be measured between that sensor and that reference electrode. And just having the right mix of constituents to make sure that it's selective towards that ion of interest, and that other ions don't pass through that hydrophobic porous matrix. That's probably one of the biggest challenges. And to and if you do that correctly and do that right, and prevent particulate matter from kind of getting in there too. Sometimes we have protective coating layers on top of it. Then the signal can be stable and can really last for weeks and up to months at a time. But if you have your membrane degrading in any way, and other ions of interest can get in there, or other dirt, or other particles get in there, the sensor can quickly degrade and foul and not operate properly anymore.
Sure. And so you say, weeks to months. And so in terms of your testing, I'm very interested in hearing some of these test results that you've had, both in terms of performance of the sensor for getting kind of the concentrations of these different nutrients right there in the soil, or even in the, in an aqueous solution. And also, how is the robustness of the sensor performed in terms of its longevity there in a soil environment, maybe versus a water environment?
Yep. So we still got to push further on the soil test, but in the water so far, we've gotten it to work up to 3 months
Wow.
continuously, just dipped into the water itself. And that's been in the laboratory setting, but we don't see that it should change too much when you'd actually put it in a stream of water.
Sure.
I think the bigger concern is just with the wetting and drying that may occur in the soil
Absolutely.
environment.
Yep.
So we'll have to see how that's the big question once we get out to the farm.
Sure.
How will it work? We've tested a wide variety of different water saturation levels for soils to try to get a feel for that, but we still,
Sure.
there's nothing like actual getting into the field and testing them, and that will really tell us.
Absolutely. And so would the idea with these sensors be to put them in around the same time that you would do kind of a soil moisture sensor that does stick out above the ground? So kind of once corn or soybeans actually got up out of the ground and emerged, you'd go and put these in, and then, leave them for kind of the 2 months where it really matters to manage your nitrogen over the course of the season. Is that the whole idea then?
Yep, that's right. Yep, so that we can, and then hopefully, yep, and then when nitrogen or fertilizer is spread on the field, we can hopefully monitor those spikes and correlate that data a bit to the soil moisture probe data as well, so we can figure out what water content was in there, and hopefully be able to correlate that to, or help us correlate the actual sensor reading to the nitrogen concentration that's there.
Sure. And so in the lab, just thinking about kind of the correlation, and you talked about some of the commercial sensors out there, that this sensor is actually performing better than some of those that are available. How well really has this sensor measured nitrate in these solutions there in the lab?
so yeah, so ours is a little bit different. So we don't have to like regenerate an electrolyte solution like you would with those liquid junction ones that the commercial ones are operating on. And the solid contact electrodes that we use can be more finicky in that it might not be harder to calibrate them, but we think we've come up with some methods to overcome those problems.
Okay.
But yeah, so since they're so simplistic, and you don't need that regeneration electrolyte, that means that they can just sit in that solution or in that soil and run continuously for very long periods of time.
Sure.
So that gives us promise or a reason to keep pushing this and to keep working on it. If we can
Yeah.
overcome some of those problems with them, that they could potentially be really long lasting ion selective sensors.
Yeah, absolutely. And I guess thinking about this practically, is that calibration issue, is that something that you would encounter only during, say, the manufacture or the lab side of these sensors, or is that something that you would have to do when you went out to the field, calibrate them, in sort of solution, and then put them kind of in the ground to continue sensing for the rest of the year?
Yeah, that's a good question. We might want to do like a 3-point calibration with them and give the person who uses them sample solutions to calibrate them
Sure.
right before they use them the first time. If you think about a pH probe in a chemistry lab, you usually have
Hmm.
some sort of 3-point calibration with known
Sure.
pH solutions, or solutions with known pH. So it may be something like that. It may be, some sort of mixture that we have to add to the sensors as we put them into the ground for the first time to help
Sure.
make that calibration. So those are things, yeah, that we'll probably have to work on and figure out.
Sure. Yeah. I mean, it kind of, with yield monitors, even I think about the fact that we try to get like a 2 or 3 point calibration, for the yield monitor, make sure that the grain flow is being measured accurately at different speeds in the fields and different amounts of grain. So it's definitely something that's, you really can't get around when you have some sort of sensor that's measuring anything in a field or a laboratory.
Yep. Yep.
So thinking about how this technology might continue to evolve, and actually, we got a question from Corey from Saskatchewan, Canada, on Twitter as we were kind of preparing for this interview, and what he wanted to know, thinking about novel nitrogen measurement sensors, is how exactly are the technologies that you've developed different from what Teralytic and some of these other maybe commercially available NPK sensors are? And I know you talked about kind of the liquid junction sensors, and I'm not sure if really that's what Teralytic offers, but I'd love for you to kind of dive into that a little bit more, what the differences are between those commercialized solutions that are out there.
Yeah, absolutely. Yeah, and I'm not completely sure what Teralytic uses.
Sure.
I'm sure that some of that's proprietary.
Yes.
And some of those other commercial sensors, but I think our recipe for creating the hydrophobic membrane and the ion selective constituents within that membrane are probably our secret sauce, so to speak, and those things help us maintain stability and prevent interference from other ions that we think is superior to other sensors. There's still a long way to go in that development, but I think that's it, and I think that's probably what researchers are working on and what those commercialize. Everyone's trying to figure out what constituents and what reagents and so forth are needed to make that membrane more stable, more selective.
Sure.
Because the overall electronics and everything else behind it are probably pretty similar.
Sure. I mean, it's, the telematic solutions are fairly standard across the board. And, it does seem like everybody's kind of using, even in soil moisture sensors, using, electrical methods of, having a reference and also measuring the actual, solute or whatever you're really trying to get out of the measurement process. So, thinking forward, what would be necessary? We've talked about that you really need to protect this membrane. What do you think is the most efficacious solution that may be available out there and necessary to kind of push these membrane-based sensors to a commercial level and maybe be a practical solution in the future for farmers?
Yeah, I think you definitely need more people working on it. That's always helpful.
Yeah, and tough in an academic position for sure.
I know, exactly, because you have such limited resources to bring this forward quickly. Yeah. But yeah, I mean, I think the membrane, there might be some filter technology that might help filter out particulate particles from reaching sensitive components within the sensor that needs to be explored as well. But the polymers that we're using and then I think many are using are pretty advanced, and I think we're getting to a point where these materials will hold up for weeks and months, and the critical months that would be important for in a farm field. So I'm hopeful that we could get them to last the entire growing season or the time during the growing season when it's needed. Sure. And then perhaps those membrane cartridges can be replaced and the electronics and the housing and so forth can be reused, of course.
Sure. Awesome. And so is this something that I think I read in one of the articles that this is kind of a collaborative project with the University of Florida, or at least at one point there was some collaboration with the University of Florida. Is there going to be an opportunity to kind of measure this in a lot of different environments, because the soil types are very different, in a lot of places in Iowa versus what they are in Florida. And, as you go internationally, I mean, it's a totally different ballgame as well. So.
Exactly. And Florida is on kind of helping us make the telemetry and the wireless electronics needed to make remote measurements in the soil. And that is part of the grant is to test them in a wide variety of soils right here in the Midwest. but also in Florida where it's more sandy or more clay
Yep.
concentrations than maybe here. So that potentially we could get an idea of, yeah, maybe different membranes have to be constructed for those different soil types.
Sure.
And that might be the next step in the research.
Sure. Yeah, that'll be really interesting, because just thinking about, how clay soils, dry out versus how other, sandier soils dry out, and how big of a change those wet versus dry extremes can have in the soil. I think that'll be a really interesting test to see how much those membranes really fatigue.
Hmm. Yeah.
So, um, so I guess another thing that I'm kind of interested in is, you're in kind of a different field, right, than agriculture, but you're still working on a lot of these agricultural problems. Is that something that you aim to continue to do in your lab with this environmental focus? And what do you think are the advantages to coming at an agricultural problem from a different discipline?
Yeah, I think it's really helped me actually, and I do want to keep this kind of multidisciplinary approach to the lab, because a lot of the things that we've developed with the wearable ion selective sensing, for example, making it flexible, form fitting to the body, making it robust and last long, can be used in those agricultural types of sensors. And a lot of times, some of the technology, sensor technology, has been kind of pushed first in the biomedical space, just because the funding is larger there, and in your ability to, the cost basis for this can be much greater, because when you're dealing with the human health, human body, products can cost quite a bit, and people are okay with that. But then the agricultural space, you can imagine, having a foodborne pathogen detection sensor. Well, if you're, what are you going to test? Are you going to test the rinse water? Or are you going to try
Right.
to test every single head of lettuce that's going through? Well, that
Yep.
sensor has to cost pennies virtually.
Yep.
So we've developed and come a long way in the biomedical space, and now I think it's time to hopefully learn how to lower the cost of some of these sensors and bring them
Sure.
to the agricultural space and really push precision agriculture. And I think that's kind of in general where the field is going.
That's really cool to hear, and it kind of connects with two other interviews that we've had on the podcast. I think about we had an interview with Ryan Regus from Bushel, and he was talking about how data can be hopefully used to kind of target health solutions, right, and kind of get people's diets in a way that is pushing for better health. It's literally targeted precision for them. And Ranveer Chandra from Microsoft brought that up as well. And then I think about Pivot Bio. We talked to Dan Brown from Pivot Bio, and he was saying that
Mhm.
really he's hoping a lot of these testing procedures that have come out of COVID will eventually make their way into kind of the biological space, and help us do more rapid testing for different microbes, in the soil and in other places. And so I think that's a really interesting interface between, biomedical and the environmental side of sensing. Um, so I guess on that front, what do you think are some of the other most exciting, besides nutrients, like some of the exciting potential for biosensors, maybe for measuring microbial communities within the soil, or something like that?
Yeah, absolutely. That's kind of been a push too. Could we monitor enzymatic activity or other parameters in the soil, to kind of get the full picture of soil health? We could do moisture, temperature, um, pH levels, different salts, concentrations, and then maybe an overall microbial health, or at least get the picture of that. So that, yeah, the idea is that you can maximize that soil health, so that you can maximize crop yields, and not kind of had these dead zones in soils where things just don't grow anymore, because it's just
Sure.
the soil's been exhausted or overworked. um,
Yeah.
yeah, that's definitely something exciting, and I think there's that's exciting. I think there's opportunities for carbon sequestration as
Huh.
well. Could we sequester carbon, or how much carbon can be sequestered in soils? Could farmers use that as potential, you know, I guess offsets for companies that do emit a lot of emissions? I know
Sure.
there's talk of that as well. So I, it's an exciting kind of dynamic thing still, and there's opportunities there for sure.
Sure. And kind of on that carbon front, I mean, do you think it is possible to actually measure maybe how much carbon is increasing within the soil with a biosensor or some other type of sensor along the lines of the technology that you've already been working with?
Yeah, we haven't looked into it yet, but it seems like there may be some promise there to somehow get the total carbon count, so to speak. It would be interesting, if we could do that. But I think those are things that need to be still further explored.
Sure. Yeah, and I want to finish our interview up here in just a minute, but there's another question that I had when you were talking about, basically the sensor would have to cost pennies, right, to measure every single head of lettuce that's going through kind of a food processing facility. In your experience, going from, and maybe just in your observations, right, of the industry, going from a biomedical application where you can afford to have more expensive sensors and getting to a low cost sensor for agriculture, what are some of the necessary steps that have to happen for a technology in order to kind of bridge that gap? Because I imagine it's pretty substantial. And I don't know if it's really more technical or more manufacturing or what really has to happen, but I'd be very curious to get your thoughts.
Yeah, I think both, in the fabrication standpoint, it needs to be something that can be scalable. So, printing technologies, things that can work in roll-to-roll manufacturing. And that would be the only way that you could really make it that cheap per sensor. So, completely automation all the way to fabricating the electrical components of the sensor, down to functionalizing it with the chemicals and biologicals needed to make it selective to whatever you're trying to detect. So all that automation and fabrication. But then if you look at, okay, that's how you need to fabricate it that cost effectively, then researchers need to look at, well, since we've been doing it so differently, or where we could manually pipette things onto a sensor, or maybe we're using silicon chips that are using clean room technology, that the same type of technology that goes into a computer chip just really wouldn't be cost effective for these mass produced sensors. So
Yep.
is there other fabrication needs that we can do? And then you have to then research ways to figure out, well, how can we still retain a high sensitivity and selectivity for the pathogens or other analytes that you're trying to detect by using these other fabrication techniques. So they kind of go
Sure.
both in hand in hand, in order to push for agricultural space. So it's definitely, we can pull things from biomedical, but we have to do more research to figure out how to make it work in the agriculture environment.
Yeah. That's super interesting. And I don't know, I think it's interesting that you brought up automation again, because it seems like in most cases right now, that automation piece is really what is the next step to a scalable solution in a lot of ways. I mean, if you think about digital ag and trying to implement precision maps, I mean, automation is kind of the next step to making sure that more people can do it effectively. And it sounds like even on the fabrication side and scaling biomedical technologies, that automation is really kind of the secret sauce there as well.
Yeah, I think so.
Yeah. So I guess as we kind of close out this interview, where would you kind of direct people to go to learn more about soil nitrogen sensing, and then also to learn more about the research that you're doing in your lab?
Yeah, that's a good question. So I definitely, you can look me up on my website. You can see kind of our latest publications and so forth on there, and we usually put the news releases. And sometimes those news press releases are easier to digest than
Sure.
the research articles.
Absolutely.
Sure. But I'm giving a talk next week at the NNI, if I will get that acronym right, but nanotechnology initiative, and it's a government forum where we talk about nanotechnologies, and we'll be talking about agricultural based technologies, and it's a webcast, or a podcast, much like this. It's called Nanosensors for Food and Agricultural.
Awesome.
Webinar. Yeah, so I
Sure.
could even give you that link as well.
Yeah, it'd be great. Do you
Um,
know if they're going to have post access on that? Because we probably won't release for another couple of weeks, but I think a lot of our listeners would be interested if they're going to do kind of like an extended access period or anything like that for people that want to go back and get it.
yeah, yeah, I think so. I think it'll be
Okay.
made public, and I could, nano.gov. It'll be on nano.gov.
Awesome.
I can give you some of these websites, but
It'd be
that
great.
kind of, yeah, yeah. So it'll have us, myself, another professor from Michigan State University, one from MIT, kind
Awesome.
of be talking about the space, and those forums are kind of the latest information on it. Yeah.
Sweet. That'd be awesome for sure.
Yeah. Yeah.
And I guess, as you continue to push on this project of doing nutrient sensing and specifically nitrogen sensing in the soil, I imagine there will be some publications and some other things coming out of that NSF grant that people can be on the lookout for, right?
Yep, exactly. Yep, we're going to be publishing another one soon on nitrate sensing, and we hope to kind of push forward with hydroponic tests as well, and
Awesome.
kind of publish those. I can always down the line send you links to those as well.
Yeah, absolutely. So I guess as we close out this episode, it's one of the things we always do is we always ask, what is somebody's final insight or piece of advice? And so what I'd like to ask you today is, what is some insight that you would like to leave our listeners with regarding like the importance of effective nitrogen management in agriculture and maybe even like working with new sensors, and maybe some piece of advice that you would offer for some of these new technologies that are coming out and becoming available?
Yeah, definitely. So if anyone who's working in the sensor field who are developing them, it's always easy, especially with these ion-selective sensors, to get the sensing range and detection limits you need. What's really difficult is selectivity, and it seems like all sensors are like that. We have a lot of research articles in the literature, and they kind of fall short because they never actually test in the biological medium that they're designed to test in. Like they'll be tested in the laboratory, but won't actually be tested in blood or saliva, or in case of environmental sensors in soil or in water environments. So really, I think selectivity is the challenge,
Sure.
and in essence also the stability and durability, because in the biomedical space it was diagnostics. This might be one test and you're done, but in the agricultural field, monitoring for weeks and months at the end is a different ballgame. So new efforts need to be made in terms of longevity for these sensors as well.
Awesome. I think that's a really good quote there to end on. And I think it's been super interesting for me. I mean, so I did my undergraduate thesis on working with hydrogels for trying to basically provide a soil amendment that nitrate could attach onto and be kind of as pH in the soil would change, basically be desorbed and readsorbed as the season went on. And the longevity of the hydrogels, in the soil was one of the major issues. How do you really measure it accurately, and also, can you actually have the right makeup of those hydrogels to degrade properly, because you want them to last about 3 to 4 months and not just stay in the soil forever. I don't know. So there are a lot of complex issues, I think, with ion selectivity and materials. So. Thank you to Dr. Jonathan Claussen for taking the time to join us today on the Farm Bits podcast. In this Zoom and work from home world that we live in, I appreciate your patience with the audio quality on this particular episode and on other episodes in the past. I hope that you're able to stick with the episode and really listen to Dr. Claussen, because he offered many interesting insights during the episode that I think are valuable to anyone who's thinking about nitrogen measurement or monitoring in a soil environment. I thought one of the most interesting aspects of the episode was actually Dr. Claussen's perspective on the crossover between biomedical and environmental sensing. He talked about how there's a lot of scalability concerns and also expense concerns that are associated with transferring biomedical technologies to environmental applications such as in agriculture, and particularly talking about, for example, you would really have to make sensors cost pennies to measure every single head of lettuce for some sort of foodborne pathogen in a food processing facility. And so I think his perspective on what it really takes to get those technologies to agriculture was really interesting, but also a lot of the crossover and some of some of the similarities between measuring, say, potassium or chloride ions that are coming out in sweat and on a wearable sensor, measuring those, but also connecting that technology to measuring with ion selectivity in the soil, such as for nitrogen monitoring and measurement. So I think there are a lot of interesting crossovers, and this is kind of a theme that's come up in other episodes as well, and it's something that we certainly should keep an eye on and maybe delve into a little bit further in future episodes of the Farm Bits podcast. So if you'd like for us to do that, please reach out to us, and otherwise we look forward to getting started on our next series in our next episode, and we look forward to having you tune in then. Thanks.
Thank you for taking the time to join us today on the Farm Bits podcast. If you enjoyed this episode, please subscribe to the podcast on Spotify, Apple Podcasts, YouTube, or wherever you listen to podcasts to be informed about the latest content each week.
We welcome your feedback, so if you have comments or questions for us, please reach out to us over email, on Twitter, or in the review section of your favorite podcast platform. Our contact information can be found in the show notes.
We'd like to thank Nebraska Extension for their support of this podcast and their commitment to providing high-quality informational material to the members of the agricultural community in Nebraska and beyond.
The opinions expressed by the hosts and guests on this podcast are solely their own and do not reflect reviews of Nebraska Extension or the University of Nebraska-Lincoln.
We look forward to you joining us next week for another episode of Farm Bits.